Good morning everyone, and welcome back to our channel. Still working on our tutorial, and we are approaching what is the true programming of a lathe, thus the execution of a sensible mechanical part. Before we start making a program consisting of roughing, grooves and threads, we need to take two notes that remind me of one thing. We must at least have some knowledge about why and how to use one tool over another. Now, I don't know if you have ever seen a catalogue from a company like Cormat. I mention several names because I don't want to advertise anyone. Ecco, Tungaloy, Vidya, Nicco tools, there are thousands of them. They have a myriad of turning tools or inserts. I hope that anyone taking a course knows at least that to work in turning, it is necessary to hold the piece with a tool that mounts an insert, generally made of carbide, to remove the chip. Now, the first question that a programmer must ask is, what type of tool should I use? A simple small example. In our examples, we had 15 degrees. Can I ever do this turn with a square insert that has 5 degrees? No, I will never be able to do it. So I will have to use, for example, a tool with 35 degrees or 55 degrees, which allows descending without working from the back, thus without removing more material in this area. So I can't explain everything that concerns tools, but at least the basic shapes. So the first one, the most well known, is the 480-degree insert with two useful cutting edges, or four if it can be turned at 80 degrees, and two recovery edges that can be used for turning bars. This is the typical insert used for roughing. This insert is usually called CNMG or CCMT. What is the difference? Now I will explain it to you. CCMT then normally inserts, if turned and viewed from the front, present two possibilities: a rectangular section or a section that we can call a bowl, where the cutting edges are. The CNMG is made like this. So if we look at it in perspective, we will see that we can use 4 cutting edges on this face and just as many on the other, meaning it is indeed reversible. The CCMT, which are called positive tools, is not reversible and can only be used on one face. It goes without saying that this is the best solution for finishing and this one for roughing. So let's look at them briefly. I have an example with me and I will show it to you. First I will draw the square, so 4 corners at 90 degrees. SNMG sometimes also changes this last letter to SNMA, which means it is flat, without a chip breaker for cast iron, or SCMT. Here I have an example of SNMG. Let's try not to mess up with the camera. SNMG is this one and SCMT, okay? I hope the camera focuses. If I turn the SNMG, you will see that it is exactly identical. If I turn this one, you see that there was no chip breaker. Because look, if you can see them, I will place one next to the other. Because the black one, the dark one, is the SNMG. You see that it has a perfectly rectangular section, while the SCMT is not a small insert that I use a lot. To a trapezoidal section from an isosceles trapezoid, because this little camera here can only be used from this side. Okay, for every type of turning insert there is always its negative version and its positive version. Negative is preferred for roughing operations which require sturdiness, while positive is preferred for finishing or the material. For example, with aluminum we only work with positive inserts, except for a few exceptions. There is always an exception that confirms the rule. Okay, then we have the TN MG triangular. I'm going from memory, but I wrote TCMT. I didn't make a mistake. TCMT, which is its positive version. I always write the negative version above, which has 6 cutting edges in this case. TCMT has 3 cutting edges, only those above. Then we have what I love, the DN MG, which has 55 angles. These 2 cutting edges are completely unusable. DN MG, DC MT is its relative, positive. And finally, we have 35 degrees. So 35 degrees here, 2, 35 degrees, obviously. This is also 55 degrees over here, 2 unusable tools, VNMG or VCMT. I don't know if you noticed. I worked many years in cast iron. In fact, I always remember the negative version by heart and never the positive, because when working with cast iron, the negative tool is the most used. Obviously, there is a whole series of tools for special operations that are not standardized with ISOMO standards. Each manufacturer has its own. The small tools for grooves are inserts that allow working in one direction only. Now they have also invented those that can push in this way. They have been around for a few years now. There is a company that calls them Grip, which is an Israeli company. They cannot make large passes, but they can widen inside the groove. Then there are the thread cutters, which are triangular inserts. A protruding tip. Luckily, I am not an artistic designer without a ruler. The thread cutters, and then all the various tips and inserts, and so on. The tips and inserts mount inserts like the SNMG, but they give them a special coding, and they are drilling tips. An interesting thing to know when you read the code of a tool like CNMG, G for example, is that it is followed by 12, 04, 08. These numbers have a meaning, significance and importance in pairs. 12 is the diameter of the inscribable circle within the shape, so this distance will be 12 and defines the size of the inserts. There are inserts of 8, 12, 9 and 19. And for heavier machining, there are also larger inserts. So don't worry, those also exist. 4 is this thickness, 0. 8 enlarges the tip of my tool 0.8 is the tip radius and is for us one of the most important pieces of information in turning, because we define the feed rates from there. Then you will find letters, and each manufacturer has its own. I will give an example with Coromat because I know it well. PF, PM, PR define the geometry, the shape of this figure that you see above, which is called the cutting edge. PF are usually cutting edges for finishing, PM for medium roughing, and PR for heavy roughing. However, these are things you will need to learn from the catalogs, along with your tool supplier. Know that not everyone has entered workshops, and I asked for an insert for cast iron, and they told me that they only look at the shape. It's not that we use just any material. In fact, every material, and even every application, has its own insert. There is no absolute best insert, because the machine can also make a difference. However, we need to try to optimize the insert for the processing we are going to do. And here, guys, only experience is required. In front of a screen, I can only give you a very general overview, and then there will be a number, 40, 25, 43, 25, that will determine the material, the type of powder, because these pressed powders are crucial, whether ceramic or quality insert that we are going to use. From here we understand if it is an insert for super alloys. Therefore, heat resistant steel, aluminum, cast iron, so material that does not produce chips like steel, and so on. Here we have what is a standard description of an insert. This is a rhombic, 1, 12 meter high, 4, 0.8 tool radius, PF, so for finishing. I shot it at home. I don't remember, it was 42. Now we are at 43.25, if I remember correctly. You will often hear me talk about Coromat because it is the most well known. That does not mean it is the best. In some cases it is, in some cases it is not. We will find excellent inserts from Tungaloy. We will find excellent inserts from Iskar. We will find excellent inserts from Kennametal. I apologize if I don't mention other names, but it's just because I can't think of them at the moment. Then there are special ceramic inserts, and there we can mention SPK. There are cutting tools, the best ones, let's say, are said to be, because I don't want to confirm it here. I say it here and I deny it here. We are talking about Iskar. There are the tools in. There are cubic boron nitride, CBN tools that are used for machining hardened materials. So guys, it's an endless world. Okay, let's start by looking at some qualities of these, some characteristics of these inserts. But geometry is not that important. So, what can we understand from geometry? As I said before, we can understand if we can make a profile like this or if we can't make it at all. Often, a profile like this uses that famous goal insert that can work from here or from there. They also exist with a round head, and it gets tricky to program. There is always a solution. Always remember that. I remember many years ago I had to make a hole, for example, and I couldn't find the solution in the insert, but I discovered the anti-vibration bar, a bar that extends 14 times its diameter. You put the insert here and it doesn't vibrate even if you pay for it. There is always a solution. You should talk to those who sell you the inserts. Never rely on incompetent people. So you can buy from tool suppliers, but always try to have connections with the distributor companies in material. So why did I say that? The insert tip is important, because if this is my insert tip, as you can clearly see, that it is never having sharp edges, but will have radii ranging from 0.4 to to 0.8212216. There are also smaller radii, which are quite small in size, including radius modo 2 and radius 2.0. However, in general turning operations, we will find this. What does it mean? It means that if I set my machining tool advance forward, setting precisely at 0.3 inches per rotation of self-centering chuck, my tool will advance forward by exactly 0.3 of an inch. Okay, so think about thread. This piece viewed under microscope. And here's tip. Let us place red dot first rotation here, next there. The distance between this tip and this tip is 0.3. You will understand that the depth from here to here, if I use a radius of 1.6, my groove will look like this, just slightly pronounced. If I used a radius of 0.4, my groove will be like this. So, the first radius is 1.6. With approximately the same feed of 0.3, radius 0.4. When we use the roughness gauge, which is the expert's roughness meter, obviously here, my gauge will pass smoothly, and here it will bounce. This is the roughness that we will achieve, explained in simple terms. There is also a formula to calculate roughness in turning, but I do not intend to explain to you because I find it utterly ridiculous to work with formulas. Why is that? Because this is fine. As long as excuse me if you are technicians and think that, and maybe I contradict you, do not want to offend anyone, but roughness varies. Yes, according to what I explained to you, but it also varies depending on the type of machine. The fact is that if you work on an ASA 6, ASA 8 or ASA 11 on a new machine with valid bearings, depending on the material, whether it is well cast or poorly cast, and the type of cutting edge, roughness is something that should not be calculated with formulas but measured in the technical office with a roughness gauge you trust. The important thing is to understand how it works. So there are two aspects that regulate roughness. Obviously, the feed rate in relation to the tooltip radius. A simple rule: for finishing, 1/4 of the tool radius; for roughing, 1/2 the tool radius as maximum values. So, I'm not saying that if you use a radius of 1.6, you will achieve a feed rate of 0.8 as maximum values. That said, each tool catalog includes a small chart with a drawing that seems to have the depth of cut on one side and the feed rate on the other, and you need to stay within this little graph. Make sure to have it explained well. Look at your catalogs and you will find it. However, it is important to understand how roughness works and to have an idea. So, if I want to do a finishing with a radius of 0.8, I will set it to 0.2 for finishing. Okay, let's start like this. Then I go to a technical office, have the roughness measured, check the drawing, and see if I'm within the limits. Additionally, I will conduct a study on the drift of tool life. That is, a tool with a radius of 0.8 after making 100 pieces will no longer have a radius of 0.8, but a radius of 0.9. This does not mean that the roughness will improve because it will wear out, so that also needs to be done. I want to establish that a user should work for 15 minutes rather than 25 pieces. I check the roughness from the first to the last and standardize the duration. So, if I require a roughness of 0.8, I will need to start at 0.6 to reach 0.8 in drift. Here lies the difference between the inexperienced person who wants to be a turner and the professional who wants to deliver always compliant pieces. Managing roughness. I am taking a programming course here. I try to give you some tips. There's a world behind it, but I don't know who invented it, so I won't name names. Someone, however, had a brilliant idea many years ago and said, what if I make the tip of the tool with a radius of 0.8 or whatever, and then I add a 1 millimeter flat here. This is my tool, this is my CN, MG, this is the magnification of this point. When I advance, I can no longer make this shape because this area will flatten out. And that's how they invented the scraping tool, also known as the Viper. The scraping tool can achieve an advancement equal to the radius of the tool with an excellent finish. Even there, the scraping tool can obviously generate vibrations. Sometimes it's fine, sometimes it's not. If you need to work with a material that requires particular chip control, it might not be suitable. What is chip control? It is ensuring that the chip breaks. I never want to see machines that produce chips 20 meters long. When I see photos of 3-meter long chips on the internet in various Facebook groups, and people say, look how cool we are, it's fine, but it makes those who haven't made that mistake laugh. However, that's not how you work. The chip must be controlled, it must break, either against the tool or against the piece. But it must always break. So sometimes the Viper can create this problem. And as a result, you go back and reuse the 0.8. Honestly, I am a huge fan of the Viper because I have experienced finishes that I didn't expect before. Okay. Well, so we have seen some importance of knowing the shapes of the tools. So, programming. Based on the tools we have, or in the drawer that we can purchase or that are available on the market that we can get. We have some tips on how to manage advancements. So if we work with a radius of 0.4, we never work with an f0.4. If we work with a radius of 1.6, an f0.4 can make sense, even 0.5 or 0.6 in roughing, and so on. In finishing, it may seem absurd, but we must never exaggerate with the radii of the tools, because then we won't have good tolerance. To maintain tolerances, two things are important, if possible, and if it's worth it. A positive insert. So, the second line of what we wrote after, a tool radius that is not too large. Unless we are doing particular machining, abundant cooling of the part is necessary because of thermal expansion. If we make a part with a diameter of 30H7, dry at 400 meters per minute with ceramic, it will be hard to leave it there to cool. And after 3 hours we find it at the same height we measured it. Therefore, ceramic is not used for large finishes. I mentioned this to give you an idea. Therefore, it is important, especially if we are working with very tight tolerances, to cool abundantly. If we are working with tolerances of 1 or 2/10, we can also work dry and aim to achieve the maximum tolerance. Okay, but these are things that are separate from a programming course. I like to talk about them, I like to share them, I like not to rush, because I hope that those who listen to me will remember one day, ah damn, but I remember that if I work with the Viper, I could have vibrations, so maybe I won't use it on a boring tool, because boring tools are more susceptible, so tools for internal work are more affected by vibrations than external ones. What machine do I work on? I work on a small machine that runs at 10,000 RPM, but can handle very little. I won't order the Vipers, I will order the 0.4 radii. I work on an 80-ton lathe AC11 with a turret as big as a house. I even use a Viper with a 1.6 radius in it. Now remember these little things for next time. Let's start. If I don't think of anything else, because sometimes I come up with something and add some more information, let's begin to look at sensible programming. So not starting from x0, z0 with some offset. Let's start to see some roughing macros, which are very interesting, and you'll see how roughing macros make life easier. And remember one thing, for now, we haven't talked about it, but if you don't clamp the part well, you can create the best program in the world, and you'll only get garbage from your machines. I thank you for being with me. I look forward to seeing you next time, and good work. Bye, thank you.